So hey guys, welcome back to the channel. This is your physics buddy, and in today's session we are going to talk about forces and motion, which is a part of unit 5, and this is going to be the third lesson on it. In this video we're going to discuss Newton's second law. We'll saw the application of weight force, drag force, and also talk about a special condition of weightlessness. Do check this video out for a few minutes and understand how important it is. Let's start. So basically in the last class we talked about weight a little. And today we are going to first of all look at some cases where the value of weight might be a little different, or what are the other forces that might be linked with the application of weight acting on a body. We already discussed what is weight. So weight is basically the force which is acting on a body due to gravity of any planet. So basically this is one such force which is acting on an object due to the gravity of the planet. So the thing which you need to understand here is that weight of the object here on Earth and weight of the object on any other planet is going to be different, because it is something which depends upon the gravity of that planet. So if you consider let's say Earth, so in case of Earth the gravity is approximately 9.81 meters per second square, or we should find this is acceleration due to gravity. Like with what force Earth is going to attract any object on its surface, it is going to be given by weight, which is the product of mass and this acceleration due to gravity. So whatever planet it is, we'll put the gravity of that planet, and weight can be simply calculated by mg to be precise. Again, it's a kind of force, so the SI unit will remain Newton. The most important part here is its direction. So weight is always acting perpendicular to the ground or surface of Earth, or it is always acting towards the center of the planet. So that is what we need to understand. Like for example, if this is the surface of Earth and there are few objects placed at different points, so the force vector here, which is given by weight, is something which is acting towards the center of the planet. So weight is always directed towards the center. That is the key point. So in all the cases, we can say when we have an object and it has certain mass, so weight is acting towards the center, and it is always equals to mg. Now let us assume few things here. So just consider an object which is dropped from a certain height. It can be any height, let's say from the top of a building, or you can say from the top of tower. So during its fall, let's say this is going to be the Earth's surface. So during its fall, what we actually observe or feel is that there must be some force because of which the object is going close to the surface of Earth, or there is always some force which is actually pulling the object towards the surface of Earth, and that force is nothing but weight, which is always equals to product of mass of the object and the gravity of Earth, that is 9.8. But apart from this, we also observe that there is some force acting on the object in the upward direction, which is known as drag force. Let's talk about this drag force a little. So drag force is any kind of force which resists the motion. So a force which actually resists the motion of any object. So what is the condition? What is the key condition of drag force to act on an object? The condition is whenever the object is moving and the drag force is acting on it, it means there must be a medium. There must be a medium. In order to understand it, let's take a very simple example. Suppose I ask you a question. So if I drop two things, like let's say one paper sheet and one ball from the same height, I assume. So which object will reach to the surface of Earth quickly?
The ball.
The ball. Reason why ball will move
because when you, I guess, multiply its mass with the gravity, it's the weight is more.
Yeah, that is one case. But another case here is that the drag force which is going to act in both the cases, it is going to be different. In the
Mm.
case of paper, this drag force is going to be very much. Whereas in case of this ball, drag force is going to be very least. So it is least in case of ball, I would say. Whereas in case of paper, the drag force will automatically be more. And because of this, the paper comes to the surface of Earth in a little late in comparison to the ball. So now we understand that drag force is something which actually opposes the change in the position of an object. It always acts whenever there is a medium. If there is no medium, there is no drag force. So most of the time when we are doing or when we are dealing with mechanics at this grade, there is the possibility that uh, there is any medium. There is no medium. That is the more in most of the cases we'll observe that there is no medium. In few mediums we'll observe that there is a medium. But whenever there is given that object is going to move in, you can say air, then the drag force will come into the picture. That is what we have to assume. Whereas when we are talking about these things directly, when we are talking about fluids, then also this drag force came. And the name of the drag force in the case of fluids or liquids is called viscosity or viscous force. So we'll talk about that force also in the different unit. But the nature of both the forces are same. That is what we need to understand. So whenever there is a medium, there is a drag force, and drag force is somewhat directly applicable on the shape of the object. So more the surface area, more will be the drag force the object will experience. That is what you have to keep in mind. So let's say there is a simple question, and the question says an object of mass, you would say 5 kg, is dropped such that a drag force acts on it. Still, it manages to move in the vertically downward direction with certain acceleration. But still, it manages to move in vertical direction or specifically vertical downward direction with 2 meters per second square of acceleration. The question is find drag force. So always remember, whenever we are talking about forces, we are always using Newton's law. So in such situations where acceleration is constant, we can directly apply Newton's law. If there is acceleration is variable, we can apply Newton's law, but the approach is going to be different to solve the numerical. So here we can simply see that object must be going downward because of this force called weight, which is acting in the downward direction and supposed to be 5 times g, I would say. Similarly, in the upward direction, there is some drag force because the object is moving in air. Still, because of these two forces, the object is managed to get an acceleration of 2 meters per second square. So the question is, how can we find the drag force? That is the question. So in order to answer this, in order to find this, remember the process. This is going to be used in each and every question here we're going to solve in mechanics related to force and motion. Remember the process always, because these questions are kind of very easy, to be honest. If you understand the concept, it will automatically become very easy. So the
Mm.
Newton's laws we have, out of those three Newton's laws, there is a the second law of Newton, which says that the force acting on an object, or you would say the external force acting on an object, is somewhat directly proportional to rate of change of momentum of the object. So basically, with whatever momentum, with whatever rate the momentum is changing, that is the thing which is directly proportional to the force acting on the object. So, all right, we understand this thing. This was the second law. So here, the F external is going to be ma. This is the outcome. We talked about this, remember?
Yeah.
So here, the external force which is going to act on the object is going to be, I would say, there are two forces. So out of these two forces, if I want to find the net external force acting on an object, so what I would do is I would find the net force of these two. So as the question says, the object is going in the downward direction, so I would definitely know that weight is going to be more than this Fd, that is drag force. That's why the object is going to move in the direction of weight. Like, it's a very simple thing, but I want you to feel this thing. Suppose if there is an object and it is there's a force acting on this force, this object is 10 newtons in this direction, and another force acting on the object is 5 newtons in the opposite direction. So just tell me what is the net force acting on the object and in which direction is it acting?
Mm. Net force is the total, right?
Net force acting on the object such that we'll see the net motion. So net force is going to be, it's kind of very simple. Now just replace the object and assume that there is a rope which is being pulled by both the sides. So
Mhm.
just like a tug of war. So in which direction the rope moves?
Well, I guess the right side because there's more force. Right?
Exactly. So basically the net force is something you can say with what net force actually the object is going to move. Like in the case of tug of war, it will make sense now. In case of tug of war, there is a rope which is being pulled by so many people
Hmm.
at once. So if I say that these people are applying 100 newtons of force in total, and these people are applying 20 newton of force in total, so this point will automatically move in the direction of more force.
Hmm.
But if we want to find the net force here, we'll say the net force is going to act is going to be 100 minus 80. That is 20 newtons. Because this 20 Newton force is the only force which is actually going to put that point into the motion.
Right.
Whereas 80 newtons and 80 newtons will cancel out. So I would say the net direction of motion is going to be this for the point. And if I want to find out that with how much acceleration it is moving, we'll simply put ma is equals to 20. If you're having the mass, we can directly count the acceleration easily. Similarly, let's come back to this case. So here the net force is going to be what?
Mm, 5 newtons to the right, moving to the right.
5 newtons towards right. Correct. So here also, now we have to find the net force. So F external is nothing but F net external. Basically, whatever force is acting on the object, but the net of it has to be taken. So the object is moving in this direction, like in the downward direction. So which force is going to be bigger, Fd or this W? Weight,
W.
W. So can I say the net force is going to be W minus Ft?
Yes.
So this is going to be equals to mass, that is the mass of this object, into acceleration of this object, which is given as 2 meters per second square. So we'll simply substitute the values here of each and every term, and we can find out Fd. So now it's your job. Just do it and tell me what is Ft here in this case.
Okay. Let me just get my calculator.
Yeah.
Well, the weight's just 10, but you're subtracting that with the drag force, right?
Yeah, we have to find drag force.
But mass times acceleration is 10.
What?
Like the mass is 5, right? And then A is equal
Yeah.
to 2. So that's 10.
10 is going to be MA, product of MA, but we have to find FD here. How can we find this? The equation was work done. Oh, sorry. Weight minus FD is nothing but mass times acceleration. So if I want to write what is W, it is going to be mg, whereas this FD I'm taking that side, where this MA is coming to this side. So negative MA is going to be FD.
Okay.
So let us substitute the values. Mass is 5, G I already told you it is 9.8 minus 5 times 2 because the acceleration is given as 2. The drag force is coming out to be 49 minus 10, that is 39 newtons. So that air is capable of exerting a force of 39 newtons on that object and reduces its speed drastically. So that sometimes helps, but that sometimes also kills, because whenever anything enters into the system, or you can say enter into the atmosphere, like outside object, because of this air only, most of the time that celestial body will completely, you can say, evaporate into the air only because of the friction offered by the air, just causes a lot of heat and burn it in midair. So there are so many applications, so many factors which is protecting Earth to make it livable. That is one such thing. So this is what drag force is. I hope this makes sense now. I'll be asking some questions with you now.
Yeah.
Just try telling me the answers. Let's start it from a very simple one. Suppose there is an object and the mass of the object is supposed to be 10 kgs. The drag force which can act on the object is maximum of 60 newtons. Question is, with what acceleration it will go vertically downward with. So try this out. I hope you can do this.
Mhm.
The information is enough to find out with what acceleration it is vertically move in the downward direction. Remember the process. Second law says F net is nothing but mass times acceleration. Net force is something which can be calculated simply using this particular fact that in whichever direction object is moving, that force is going to be much or more. So that minus the smaller force will give us the net motion, which is supposed to be mass times acceleration. So this will give you which is required, that is acceleration.
Okay.
See, if these things actually make sense, like we actually feel them, these are very easy yet interesting because when you
Mhm.
are solving more number of problems, you'll be able to feel more of these things. So that is the best way to learn physics, to relate whatever is going on, because this physics of grade 11, I would say, it is very practical because whatever you are going to do, whatever you're going to find, it is something which is already there. You can feel it, you can watch it. Whereas in 12th grade, it's a little different.
Mhm.
Is your dad home?
My dad, yeah, so
Yeah, just connect with him once we're done with the class.
all right. It's at 3.8.
Let's verify because I don't know the answer. But yes, we can solve. That is going downward definitely. So mg minus fd is going to be ma. So let me take g as 10. Or if it is 9.8, it doesn't matter. 10 basically helps in calculation, make it easier.
Mhm.
Minus m a is something we have to find. Fd is already given as 60 newtons, so it is going to be 10 times a. So a will come out as 4 meters per second square. What was your answer?
Oh, mine, it was 3.8. Yeah, that's because I used 9.8.
Okay. 38 by 10. That is 3.8. Yeah, correct.
Mhm.
So after drag force, we need to understand what is apparent weight. It is kind of similar to drag force, but apparent weight is something which you can actually feel in lift. But in order to understand it, we need to understand one thing. A force which is applied by the surface. So we studied about Newton's third law. What was Newton's third law?
Mhm. Can we only do second one?
Okay. Yeah, all right. We did only second law. So Newton's third law says that every action has an equal and opposite reaction. That is a basic, you can say, statement. We must have heard it like tens of times. So here, when the object is kept on a surface, it will apply weight in the downward direction because Earth will always apply gravity. There will be a weight. That is why the object is sticked to the surface, or you can say the Earth. We have to do some work, or we have to actually apply force in order to move things because gravity is constant force. It is acting always. So the surface will show a reaction to this weight. So this is an action. So Newton's third law says if there is an action, there is a reaction.
Mhm.
So surface will apply or will exert a reaction, will show a reaction, and that reaction is called normal. So from the same, you can say the contact, we can say that there is a normal acting in the upward direction. So that normal is a force, which is supposed to be a reaction force. Mg is always equals to negative of normal. Again, normal is a force. Why we call it normal? Because it is always perpendicular to the surface. Always perpendicular to the surface. That's a different thing in comparison to the direction of weight. Although it is always perpendicular, but with respect to the surface. But in case, or you would say, in case of surface and ground, to be precise, ground can be different, surface can be this, or surface can be whatever. Anything is possible. But if it is ground, it should be a straight line like this. So weight is always perpendicular to this, like ground. and normal is always perpendicular to the surface. So in this case, ground and surface both are same thing. But in this case, ground is this and surface is this. So normal will act perpendicular to the surface, whereas weight will act perpendicular to the ground. So they are not going to be same. This is a case we'll discuss it in the upcoming classes. I just gave you a little idea about that how weight and normal, or you can say the reaction, actually acts.
Mhm.
So apparent weight is something which we can understand by this fact that what weighing scale show, what weighing scale show if it is operated in a lift or in any other moving, you can say, mechanism which is going against the gravity or with the gravity. Because in that case only apparent weight will be there. Or otherwise, if it is moving parallel to the ground, there is no apparent weight. It is going to be same every time. So let's visualize this thing. Suppose you are in a lift and you want to weigh. So you are standing on a weighing scale. And this lift is going downward with an acceleration of 3 meters per second square. And your mass is around 40 kgs, as I say. So the question is, what is the reading of weighing scale? So here we have to understand that what weighing scale actually measures whenever we use weighing scale. So what is the weight, by the way? So are you trying to remembering it or what?
Yeah, wings go. It shows if it's okay.
No, I'm asking what is the weight? Like when did you measured it last time?
Oh, it's mass times gravity.
What was it?
Oh, so
I'm
it's 40.
asking what was the reading when you actually weighed yourself?
Oh, myself. 165 pounds.
165 pounds. Okay, and what it is going to be in kgs?
I guess that's. I think it's times 2.2.
I guess it is around 50 kgs
75.
roughly.
Yeah,
75 more.
yeah, approximately 75.
How did you told? How many pounds?
165.
Okay, yeah, 165. So I would assume, not assume, your weight is 75 kgs, let's say. So weighing scale actually measures this weight, measures this mass, or you can say the weight, by actually calculating normal force. So whenever it is stable, like weighing scale is kept on the surface, which is not moving, it always measures the normal, which is correct. Because normal in this case is always equals to weight. But what if the object or the weighing scale is taken to be lift? The whole scene is moving now with certain acceleration. So whatever this weighing scale is going to be measured, that thing is called apparent weight. Now, does this make sense?
Yeah.
So we have to find what is the reading of the scale. So the diagram which we are drawing actually again and again, such diagrams is called free body diagram. A
Mhm.
diagram, or you can say something like, it always represents the forces acting on the object. Whatever forces are acting, we are going to represent it using the FBD to be precise, free body diagram. So here we can see the force is going to be acting in the downward direction is weight, and the upward direction is going to be normal. And this normal is something is called apparent weight. So we have to learn what is normal acting here in this case. And this is the acceleration, which is supposed to be 3 meters per second square. So we know, we just learned, or we already understood this fact that the net force acting on the object is going to be m times acceleration. So we have this acceleration here. So we can use this equation. And sometimes if it is not, we need to have a net force. We can find it. So here F net is going to be, as this lift is going in downward direction, so W must be greater than normal. So W minus N is equals to mass times A. So here we can easily find out what is the weight, like by writing mg. So it is 40 times 9.8 minus N, 40 times 3. So 40 times 9.8 minus 40 times 3 is equals to what? N. And this is something we call apparent weight. I just try to understand the application in the last case and in this case, how we are actually applying this relation F net is equals to mf. We just have to figure it out that which force is actually causing motion. So that is going to be the bigger force. Whatever force is acting in the opposite direction of that force is going to be subtracted from that force, which is bigger. And it is equals to ma. We can find out the acceleration of the whole system by calculating the net force. So normal is going to be 40 times, I would say 6.2. No, 5.8. 40 times 5.8. So this is going to be 223 newtons. That much normal or that much apparent weight is that much apparent weight this weighing scale is going to measure. So this is the apparent weight, and we can simply find it out by simply dividing the whole number by 9.8. So we'll get the apparent weight measured by the scale. So this is the concept, like that much concept is there, but the application is very huge. You need to understand the application part very well by doing questions always. So let's do some problems. So whatever we have learned so far, we need to keep all of those things in mind, because when a question came, when a good or tricky question came, almost every force is acting on the object. And we have to figure it out that what is the net force acting on the object by resolving the forces, and then what was the net acceleration. So in order to do that, we need to understand, or we need to remember each and every concept so far we have learned here in this unit. So we have to find momentum of each system. So here the momentum is going to be mass times velocity. We already know what is momentum. It is product of mass and velocity. The first and second figure is identical. It is also mv. But in the third figure, it is going upward. Again, it is going to be mv, but it is in forward direction. It is in upward direction. So for forward direction, we generally use I cap. And in upward direction, we'll use j cap. I didn't told you about this because I haven't seen it so far, but I don't know whether it was needed or not. So this x-axis is generally represented by I cap whenever we are representing a vector, because vector is something which has direction, and that direction should be shown, whereas y is supposed to be j cap
And I think
and
you
z
told
is
me about
supposed
this
to be
when we
k
were
cap.
learning how to multiply vectors.
Okay, if you know it, then it is easier.
Mhm.
Positive x-axis is I cap, negative x-axis is negative I cap. The direction will be reversed. The negative sign will show it. So this is how we can answer this change. Now try to find out this thing. Find change in momentum. What is the change in momentum? How can we find it? So we know, we talked about this thing earlier, that whenever we are going to find out the change is always final minus initial. Like whatever value of momentum is there initially, that should be subtracted from the final value of momentum after the change. So initially the ball was going in this direction with v velocity. The question says, what is the change in momentum? Ball drop dead on striking. So in the first case, if the ball reaches here, it just dropped dead like this one, came to the floor. So in that case, the final velocity is going to be 0, whereas the initial velocity is v. So final momentum is m times 0, whereas initial momentum is going to be mv. Now v is a vector quantity, velocity is a vector quantity. So every time we are going to represent or write vector quantity, we have to consider the direction as well. So velocity is supposed to be in positive x-axis. So it is supposed to be taken as I cap. So v I cap. That's why I have just written v. So the momentum change is going to be mv in the first case. Whereas in the second case, ball rebounds with the same speed, question says. So if it rebounds with the same speed, I can say after this, the ball is moving in this direction with velocity v. Now, when you are finding change in momentum, so it is again going to be P final minus P initial, but P final is written as M negative of V. Why? Because its direction is negative I cap. So V is something which becomes negative. Negative times mv again, because velocity initial direction initially is in this direction is positive v. So negative mv. So negative mv minus negative minus mv. It is going to be twice of negative mv. So change in momentum in this case is double in comparison to the first case. So in extreme cases, you have to find the momentum first by assuming these things. In whatever time that momentum change has taken place, it will give us ultimately force. Or you can say automatically it will give us force. So that is what we have to do. Another question. Now just think about it and tell me. You can answer this one now.
Mhm. Mm, probably. Hold on. Iron Ball.
Think again. A rubber ball and iron ball. So the last question we saw this thing. Then when the object drop dead while striking, the momentum changes less. Whereas when the ball rebound with the same speed in the opposite direction, the momentum changes pretty much. So this is something you can understand by this fact that if you drop a crazy ball, let's say rubber crazy ball,
Mm,
just with some force, it bounces back with a huge velocity. So here the change in momentum is huge. Whereas if you drop a iron ball, it will not bounce. It might drop dead. So it will have a less change in momentum. So the answer is going to be rubber ball. You have to
yeah.
understand what momentum change is. It actually not explaining that what velocity the object is moving. It actually explains that what force that object can actually apply, because the force is change in momentum per unit time, and that change in time is very small, milliseconds, I would say. The force is huge. Whereas in the iron ball case, uh, it won't did that much force. It won't apply that much force if it is dropped that way, because it drops dead. That
Okay.
is the case. Uh, Try this one out. You can solve this question now.
Okay. Is it C?
How you did this?
I use Newton's second law of motion. F equals ma.
Yeah. So what you got? What you applied?
So force is the 10, and then acceleration is 1. So 10 equals 1 times. Wait.
Yeah,
Yeah, I mean, sorry, m equals 10 divided by 1. So m equals 10.
got it. Now just think about this question.
Okay.
The change in momentum thing, it need to be understand. If you understood that thing, you'll understand that how force is actually acting on the balloon. Then you can calculate it as well. Let's solve this question, and you
Mm,
have to understand the process. Let's see if it is correct. So the balloon has 2 grams air. So it has given as mass, but it is 2 grams only. In order to find out answer in newtons, we have to convert this grams into kgs. It is going to be 0.002 kg. So mass is given. The question says a small hole is pierced into it. Air comes out with a velocity of 4 meters per second. So the velocity of air is also given as 4 meters per second. If the balloon shrinks completely in 2.5 seconds, the average force is going to be. We have to find the average force, and that the time is also given, that in what time that change has taken place. So again, we have to use the second law, that's for sure. But how? So initially, the balloon was pierced. Air is coming out with 4 meters per second of velocity. And finally, it has completely lost all the air in it. Velocity of air is going to be zero.
mhm.
So change in momentum, if I talk about, I try to find it out, or if I'm able to find it, then finally velocity is going to be zero. So momentum is going to be zero. Initially, it is mass times this 4. So 0.002 times is 4. So 0 minus 0.008. That is negative 0.008 is the value for change in momentum. Now what is force? According to Newton's second law, force is delta P by delta T. A change in momentum by change in time. The second law says this thing, then only we got F net is equals to ma. But if change in momentum is given, we can also find out what is the net force acting on the object. This is another way of finding force, net force on the object. The delta P is negative 0.008 and the delta T is 2.5. So we solve it, let's say. So 0.08 by 25. This is going to be the value. 8 by 2, 500. So it is going to be, I would say, 80 by 25 into 10 to the power minus 3. This is roughly around 3.2 into 10 to the power minus 3. So this is the value of force, that too in newtons. So 3.2 into 10 to the power minus 3 is going to be, like, this point has to be shifted 3 decimal places, like that. Initially, it was here. -3 means we have to shift this point 3 places back. So 1 through 3. So here it came. So 0.0032 newtons is the answer. That is this, the option. So this is another way of applying the same law. So I guess now this covers the entire thing about this Newton's law, because this is the major thing that we have to study here. Apart from this, there are few things, but they can be easily understood in various ways, or you can say quite easily.
Okay.
In the next class, we'll talk about Newton's third law of motion, and we'll say